Welcome to Section 3, Lesson 7. Across the previous 6 lessons, we built the entire toolkit for solving linear equations and inequalities, including the inverse operation procedure with reverse PIMDAS, the gather step for variables on both sides, the literal equation procedure for solving in terms of letters, the flip sign rule for inequalities, and the connective interpretation for compound inequalities. Today we add one more piece to the linear toolkit equations containing the absolute value operator. Absolute value introduces a small case split into the solving procedure, but the underlying inverse operation logic stays exactly the same as before. The case split is the only conceptually new piece, and once you internalize it, you can solve every standard absolute value equation in the rest of the algebra course in under a minute. First idea on the board. The absolute value of a number is its distance from 0 on the number line, always reported as a non-negative quantity. The absolute value of 5 is 5, and the absolute value of -5 is also 5, because both numbers sit 5 units away from 0. The notation is 2 vertical bars surrounding the expression, written as bar x bar or bar 2x minus 3 bar. Recognizing the absolute value notation on any equation tells you immediately that a case split will be needed at some point in the solving procedure. The case split rule for an equation of the form absolute value of expression equals k, where k is a positive number, splits into two cases. Case 1 is expression equals positive k. Case 2 is expression equals negative k. The split happens because the absolute value operator hides the sign of its input, so any value that is k units away from 0 satisfies the equation. Both cases must be solved separately, and the final solution set is the union of the two case solutions. This is the only structural change from the equation solving you already know. Third idea. Always isolate the absolute value expression on one side of the equation before performing the case split. If the equation is 3 times the absolute value of x plus 1 minus 2 equals 10, the first step is to add 2 to both sides and divide by 3 to isolate the absolute value, giving absolute value of x plus 1 equals 4. Only after the absolute value is alone on one side do you perform the case split into x plus 1 equals 4 and x plus 1 equals negative 4. The order is non-negotiable: isolate first, split second. Performing the split before isolation can give wrong answers and confuses the procedure unnecessarily. The absolute value of a number is the distance from 0 on the number line, always non-negative. The notation is 2 vertical bars surrounding the expression. Recognizing the absolute value operator on any equation immediately tells you that a case split will appear at some point in the solving procedure after the absolute value is fully isolated on one side of the equation. Here is the case split rule. For an equation of the form absolute value of expression equals k, where k is positive, the equation splits into two simple equations: expression equals positive k and expression equals negative k. Both cases must be solved separately, and the final solution set is the union of the two solutions. The split happens because absolute value loses sign information, so two different signed values produce the same absolute value. Step 1 in the workflow. Always isolate the absolute value first using the inverse operation procedure from previous lessons. Treat the entire absolute value expression as a single chunk, the way you treat a parenthesized chunk during distribution. Apply inverses to both sides of the equation in reverse PEMDAS order until the absolute value is alone on one side and a numerical value is alone on the other. Step 2. Once the absolute value is isolated as absolute value of expression equals k, check the sign of k. If k is positive, perform the case split into expression equals positive k and expression equals negative k. If k is 0, the case split collapses to a single case expression equals 0 with one solution. If k is negative, no real solution exists because absolute value is never negative. In this case, write no solution and stop. Step 3. Solve each of the two cases separately as a standard linear equation using the Section 3 machinery. The two case solutions together form the complete solution set, written as a list with the connective or like x equals 5 or x equals negative 2. Verify each solution by substituting back into the original equation including the absolute value and confirm both sides equal the same number. The verification catches sign errors and confirms that both cases produce valid solutions. Here is the first worked example. Solve the absolute value equation. Absolute value of 2x minus 3 equals 7. The absolute value is already isolated on the left side and the right side is the positive number 7, so we can perform the case split immediately without any preliminary isolation work. Step 1. Confirm that the absolute value is isolated. The left side is absolute value of 2x minus 3 with no other operations on the absolute value chunk. The right side is the constant 7, which is positive, so the case split will produce two valid linear equations. Isolation confirmed and the case split is the next move. Step 2. Perform the case split. Case 1 is the inside of the absolute value equals positive 7, 2x minus 3 equals 7. Case 2 is the inside equals negative 7, 2x minus 3 equals negative 7. Each case is now a standard two-step linear equation ready to solve with the lesson 2 procedure. Step 3. Solve case 1. Add 3 to both sides of 2x3 equals 7 to get 2x equals 10. Divide both sides by 2 to get x equals 5. Case 1 solution is x equals 5. Solve case 2. Add 3 to both sides of 2x minus 3 equals negative 7 to get 2x equals negative 4. Divide both sides by 2 to get x equals negative 2. Case 2 solution is x equals negative 2. Step 5. Verify both solutions by substituting back into the original equation. For x equals 5, absolute value of 2 times 5 minus 3 equals absolute value of 10 minus 3 equals absolute value of 7 equals 7. For x equals negative 2, absolute value of 2 times negative 2 minus 3 equals absolute value of negative 4 minus 3 equals absolute value of negative 7 equals 7. Both substitutions produce 7 on the left side, matching the 7 on the right side, so both solutions are verified. So the solutions are x equals 5 or x equals negative 2. The big lesson from this example is the case split discipline applied to a clean already isolated absolute value equation. Two cases, two standard two-step solves, two solutions joined by OR. The verification step uses the absolute value definition directly and confirms both solutions satisfy the original equation. Build the case split habit on every absolute value equation and the workflow becomes a fast, reliable reflex within a week of practice. Here is the second worked example. Solve the absolute value equation 3 times the absolute value of x plus 1 minus 2 equals 10. The absolute value is not isolated yet because the chunk is being multiplied by 3 on the outside and then 2 is being subtracted on top. The first task is to isolate the absolute value before any case split can run. Step 1. Isolate the absolute value using the inverse operation procedure on the absolute value chunk treated as a single object. The chunk has multiplication by 3 and subtraction of 2 on the outside. Reverse PEMDAS says undo the subtraction first by adding 2 to both sides, then undo the multiplication by dividing by 3. Step 2. Add 2 to both sides of the equation. The left side becomes 3 times the absolute value of x plus 1 minus 2 plus 2, which simplifies to 3 times the absolute value of x plus 1. The right side becomes 10 plus 2, which equals 12. The equation is now 3 times the absolute value of x plus 1 equals 12. Step 3. Divide both sides by 3 to undo the multiplication. The left side becomes 3 times the absolute value chunk divided by 3, which simplifies to absolute value of x plus 1. The right side becomes 12 divided by 3, which equals 4. The equation is now absolute value of x plus 1 equals 4. The absolute value is fully isolated and the right side is the positive number 4, so the case split can proceed. Perform the case split. Case 1, x plus 1 equals positive 4, giving x equals 3 after subtracting 1 from both sides. Case 2, x plus 1 equals negative 4, giving x equals negative 5 after subtracting 1 from both sides. Step 5. Verify both solutions. For x equals 3, 3 times absolute value of 3 plus 1 minus 2 equals 3 times absolute value of 4 minus 2 equals 3 times 4 minus 2 equals 12 minus 2 equals 10. Match. For x equals negative 5, 3 times absolute value of negative 5 plus 1 minus 2 equals 3 times absolute value of negative 4 minus 2 equals 3 times 4 minus 2 equals 12 minus 2 equals 10. Match. Both solutions verified. So the solutions are x equals 3 or x equals negative 5. The big lesson from this example is the strict isolate, then split order on harder absolute value equations. The isolation step uses the standard reverse PIMDIS inverse procedure on the absolute value chunk treated as a single object. Only after the absolute value is alone with a positive number on the other side does the case split run. Skipping the isolation and trying to split while the absolute value is still wrapped in other operations is the most common error on this type of equation, and the cure is the deliberate isolate. First habit you build today through repetition on a few dozen practice problems. 3 mistakes that catch every algebra student during their first weeks of absolute value equation work. Each one is fixable with a small explicit habit applied on every absolute value problem. First mistake: solving only the positive case and forgetting the negative case during the case split. A student looks at absolute value of 2x minus 3 equals 7 and writes only 2x minus 3 equals 7, getting x equals 5 and stopping there. The negative case 2x minus 3 equals negative 7 also produces a valid solution at x equals negative 2, but the student misses it entirely and submits an incomplete solution set. The fix is to write both cases on the page explicitly before solving either one, so the negative case is impossible to forget. Second mistake: performing the case split before fully isolating the absolute value chunk. A student sees 3 times absolute value of x plus 1 minus 2 equals 10 and immediately writes x plus 1 equals 10 and x plus 1 equals negative 10, treating the right side 10 as if the absolute value were already isolated. Both case answers are wrong because the multiplication by 3 and the subtraction of 2 on the outside were never undone. The fix is the explicit isolate. First habit: apply inverses until the absolute value chunk is alone with a number on the other side, then split. Third mistake: performing a case split when the right side is negative and the equation has no real solution. A student sees absolute value of x minus 4 equals negative 3 and case splits into x4 equals positive negative 3 and x minus 4 equals negative 3, producing fake solutions x equals 1 and x equals 7. But absolute value is always non-negative, so the equation has no solution at all, and the correct answer is the symbol or phrase no solution. The fix is to check the sign of the right side after isolation. If it is negative, write no solution and stop without splitting. Absolute value equations appear constantly in measurement, estimation, and distance contexts across science, engineering, and everyday life. Anywhere a quantity must be characterized by its magnitude regardless of sign, an absolute value equation is the natural modeling tool. 4 broad sectors below. In engineering tolerance specifications, the boundary of an acceptable measurement range is described by an absolute value equation. Absolute value of measured value minus nominal value equals maximum tolerance. The two solutions of this equation give the upper and lower acceptance limits, exactly as the case split produces. Engineers use this equation to compute tolerance band edges on every spec sheet they write, and the case split structure shows up directly in the resulting upper and lower bounds. In statistics and machine learning, the absolute error of a prediction is computed as the absolute value of the predicted value minus the actual value. fitting models to minimize total absolute error, or solving for parameter values that produce a given absolute error level. Both use absolute value equations directly. The mean absolute error metric is the average of these absolute differences across many predictions, and reasoning about its behavior requires the same case split logic that we covered today. On a number line and in any one-dimensional measurement context, the distance from one point to another is the absolute value of their difference. Solving for points that are exactly a given distance from a fixed reference point is an absolute value equation, and the two solutions correspond to the 2 points that satisfy the distance condition, one to the left and one to the right of the reference point. This pattern appears in physics, chemistry, finance, and everyday measurement. In navigation and computer graphics, the Manhattan or taxicab distance between 2 points is the sum of the absolute values of their coordinate differences, written as absolute value of x difference plus absolute value of y difference. GPS systems, robotics, path planning, and image processing, edge detection all use absolute value distance metrics extensively. The case split discipline you built today is a small piece of a vast computational toolkit used across modern computing. 3 things to take with you from this lesson today. Absolute value equations are the gateway to a small but important family of solving techniques that recurs across statistics, engineering, computer graphics, and navigation, and the case split discipline transfers directly into the inequality version we will cover tomorrow. First, the absolute value of a number is its distance from 0 on the number line, always non-negative. An absolute value equation of the form absolute value of expression equals k, with positive k splits into 2 cases: expression equals positive k and expression equals negative k. Each case is a standard linear equation solved using the section 3 machinery, and the 2 case solutions together form the complete solution set joined by OR. Second, always isolate the absolute value chunk on one side of the equation before performing the case split. Treat the absolute value chunk as a single object during the isolation phase, applying inverses to undo any multiplications, divisions, additions, and subtractions on the outside. The order is non-negotiable: isolate first, then case split. Performing the split before full isolation produces incorrect case equations and wrong final answers. Third, after isolation, check the sign of the right side. If it is positive, proceed with the case split as usual. If it is 0, the case split collapses to a single case with one solution. If it is negative, the equation has no real solution because absolute value is never negative, and you write no solution and stop without splitting. The sign check is fast and prevents the most common incomplete solving error on absolute value problems. Coming up next, the lesson called Absolute Value Inequalities, where the equals sign is replaced by an inequality and the case split logic interacts with the AND or connectives from Lesson 6. Absolute value inequalities combine every section 3 skill into one final solving procedure that wraps up the linear equation chapter cleanly and prepares you for the coordinate geometry work of Section 4.